My name's David Reid. I am one of the electrical and mechanical design engineers here at Mesh Energy. We're a small engineering consultancy based in Farnham and Surrey. I'm just going to quickly go through some basic housekeeping before we start this morning. I would ask you please to keep your microphones on mute throughout the webinar. This is simply just a courtesy to other users. Sometimes we've had problems with sort of background noise from people unmuting themselves. If you've got any questions at any time during the webinar, please feel free to put them in the chat box. I will probably pick them all up at the end. We've got quite a few people booked on for today's webinar, so doing them as we go might not be practical. And thirdly, this webinar is being recorded. If you want to see a recording or if you want to share it with any of your colleagues, then the webinar is usually uploaded a few hours after we've completed online. Okay, so short introduction about what we're going to do today. We'll just quickly touch on who Mesh Energy are. I'm sure an awful lot of you will have seen our webinars previously, and we'll be familiar with that. A little bit about the energy hierarchy, some of the basics around PV, including what it is, some of the definitions and terminology, and a little bit about AC and DC electricity, because that's all quite key. Then we're going to a little bit more of the tech, so some of the system components, some basic schematics, integration of backup batteries, which is becoming increasingly popular. The effects of azimuth and pitch, we'll define azimuth in the definitions part. Effects of geographical location. Obviously, being as we're a UK-based consultancy, that'll be fairly UK-centric, but the same will apply for locations all around the world. A little bit about islanding. So that's not about the UK. That's an electrical islanding. Controls and monitoring, because obviously that's important. And then we'll get into some of the more sort of financial side, including warranties, first of all. Then the requirements of the distribution network operators, that's the electrical operators, and then a little bit about the investment case. That will include a section on time of use electricity tariffs, which are becoming increasingly popular in the domestic market now. So we'll touch on that a little bit, especially how that interacts with solar PV and batteries. And then finally, to sort of round off the webinar, we will look at some of the key points to take away. So, you know, the kind of these things, the things that you really should know by the end of the day, and then a little bit about how we work, how we interact with our clients and developers and architects. And then obviously we'll always leave a good chunk of time at the end for questions. And so, as I say, please pop your questions into the comments box as we go, and we'll pick them up at the end. So there's quite a few slides to get through, so I'm not going to spend a huge amount of time on the bit about who we are. Most of you will be familiar with us, but we are a low energy building consultancy. So we look to partner with people to design low energy, low carbon buildings. And basically the way we do that is we look to sort of cut away a lot of the noise around renewable energies. And a lot of you know, there's a lot of claims, counterclaims about different technologies. What we try and do is just give sort of honest, simple, implasterable advice about what the best combination of technologies is for any given project. We're not affiliated to any technology. We're not affiliated to any manufacturers. We simply give honest, impartial advice. So that leads us on quite neatly to this slide here, which talks about the energy hierarchy. And this really should be the starting point for any green project. So what is the energy hierarchy? What it is basically telling you what order should you do things in to get the best result. And if we start on the left-hand side here, we'll talk about building type and orientation, and then going through things like using high energy, high efficiency materials, controlling daylight and ventilation and those kind of things. And things like the renewable technologies like solar PV actually come quite low down the list, because actually if we've got an inherently efficient building, we shouldn't need to apply too much technology to it to make it work. And quite often what happens is people leap for the technology before considering the simpler things like adding insulation or putting double glazing in, or sort of quite simple stuff. So let's have a look at some of the basics. Now we know that this shouldn't be your first port of call. This should be quite a way down the line. Let's have a look at some of the basics about this particular technology we're talking about today, solar PV. So what does it do? So basically, solar PV is a system where you have light collectors that sit on the roof or in a field. Sunlight shines onto them and they generate electricity. Now that electricity can be used on site. It can also be exported back to the grid to power other users of electricity. But in a basic sense, if the sun's out, then the system will be producing energy, and that electricity needs to be used or stored for use at a later time. The way that it's actually integrated can be done in lots of different ways, and we'll look at some of those ways as we go on. So I'm going to talk a bit about some of the definitions and terminology, because I think it's quite important that we don't confuse different things. So one of the so start with some of the sort of basics. So a solar module or solar collector is basically a solar panel, and we'll talk about collectors, we'll talk about modules, we'll talk about panels, but they all basically mean the same thing. It's the bit the light shines on that creates electricity. We'll then talk about inverters. So the electricity that comes out of a solar panel isn't directly usable by most equipment that you'll have around a home or in a commercial environment, because the electricity that comes out of a solar panel is DC electricity, and we need AC to power most machines. A string is basically a group of modules or a group of panels that are electrically connected together, and in most cases you will find that a string will have maybe 10 or 12 panels in it, and those panels are electrically connected together, and then they go into a single input in the inverter. The azimuth is basically the orientation of the panel from due south. So we're in the northern hemisphere in the UK, so the closer we can angle panels to due south, basically the better the output of the solar PV array will be. And then we have pitch, which is the angle from horizontal of the panels. And in the UK, the ideal pitch for a solar panel is between sort of 30 and 40 degrees. As you get closer to the equator, that angle flattens off, and as you get further away from the equator, that angle increases. So if you were up in northern Sweden, you'd probably find it maybe 50 degrees. If you were down somewhere near the equator, then it might be closer to horizontal, maybe 10 or 20 degrees. Okay, so next is more about the nomenclature of some of the measurement units that we use. So the first one is energy, which is the capacity for something to do work, and that's measured in joules, and 1,000 joules is a kilojoule. And then we talk about power. So power is the rate at which energy is being transferred, or the rate at which work is being done. So it's quite simple. So a joule per second is equal to a watt. 1,000 watts is equal to a kilowatt. And usually what we do is we measure solar PV in terms of the maximum power it can give under sort of standard conditions. So you'll see that panels are rated, and it'll say in little brackets at the end STC, which is standard temperature conditions. And The only other thing I'm going to talk about today, which we might talk about, is battery capacity, and that is the capacity of the battery to hold energy. So that is actually a measurement of joules, but because the number would be so enormous when you talk about it in terms of joules, what they do is they talk about it in terms of power and time, which actually, when you cancel it all out, it actually goes back to joules. But it talks about it in terms of kilowatt hours. So 1 kilowatt hour is actually equivalent to 3.6 million joules of energy. So you can see if you've got a sort of 15 kilowatt hour battery, then you're talking about very big numbers of joules, which just become impractical. So hence why kilowatt hours are used. A kilowatt hour is also, when you get your electricity bill and they talk about a unit of electricity, that is also a kilowatt hour. So the monetary value of a kilowatt hour of electricity to buy from the grid at the moment in the UK is about 15 pence. If you're selling electricity back to the grid, then you'll get a rate of typically around 5 pence. So you'll see there's a 10 pence difference there in between what a kilowatt hour of electricity is worth if you sell it and if you buy it. So I've already touched on DC and AC, but essentially DC electricity is this red line here. So you get a constant voltage and a constant current at all times. And that's what you get out of solar panels, and that's what you need to put into batteries. And it's also what you get out of batteries as well. So but what we get from the mains is alternating current, which is this green line here, and that means that the voltage fluctuates. And in the UK, we will see 50 hertz, so 50 fluctuations this voltage per second. So from a peak voltage up here to the minus peak voltage down here, and that's what you actually use in your household appliances. Okay, so let's get into some of the tech, and we'll start by looking at some of the different components within the system. So I've already talked about PV panels, and here is a pretty large commercial installation on a flat roof of PV panels. So these are the most common type of solar collector. So they're pre-formed in a factory, all the internal wiring is done, and they're relatively cheap to buy. And I say relatively cheap, panels vary in price quite a lot, and what you'll find is that at any given moment the market there'll be a sweet spot in the market about where you'll get the best output per pound you spend, and at the moment that's at around 360 watts at peak for a panel, and that's based on a 60 cell panel, which is the sort of standard domestic size, which physically measures about 1650 by 990 millimeters. And the reason that 60 cell panel is very popular, and there are other sizes available, 66 cell and 72 cell are also quite popular, but the reason that 60 cell panels are particularly popular is that they're small enough that one person can lift them, but big enough they give you a pretty decent output. If you go smaller than that, then you start ending up with too many panels, and if you go bigger than that, then you end up having to have two people to lift them, and then it starts becoming a bit of a faff to fit. But the panels physically can be mounted to buildings or onto the ground, lots of different ways, and we'll look at some of those in a moment. So the sort of other major type that we're seeing in domestic markets increasingly is solar tiles. So this roof here is a solar roof. So this is effectively lots and lots and lots and lots of little tiny solar panels all wired together, and they are designed to replace conventional roofing materials. And what they do is they lock together as a frame. You put them on in much the same way as you would conventional roofing materials. Tesla make an excellent system which isn't actually available in the UK yet, but Tesla's route to market in the US has been to go to roofing contractors rather than PV contractors, because what they're saying is basically this is a roofing material which happens to produce electricity, rather than being an electricity producing system that happens to be a roofing material. What they do is they size each of the little modules that they have to match the roofing materials that they're designed to replace, and they're designed to color match really well as well. So we'll talk about that. The one downside of, or two downsides of tiles is that they are less efficient than standard panels, and they are more expensive than standard panels. And because they obviously require replacement of all the roofing materials, they're not particularly great for retrofit, because obviously most people don't want to strip all the tiles off their roof and start re-roofing their entire building just to put solar in. We'll now look at some of the other ways, some of the ways that the systems are actually physically mounted. So this is actually a green roof. You can see here. This photo was provided by Bowder, who are one of the big green roofing manufacturers. But this photo shows how solar can be integrated into, say, a flat green roof. But actually, the mounting systems are pretty similar, whether it's a green roof, whether it's a conventional flat roof. And most PV arrays that go onto flat roofs use a ballasted system. So there's no physical anchors of the PV panels to the roof. So there's no penetration through the weathering surface. And that's quite important because obviously flat roofs tend to have water and things sitting on them, and any hole you make in that is a potential point of failure. So generally speaking, people prefer to have a ballasted system on a flat roof. Couple of things to note with ballasted systems and any PV installation on a flat roof is, the first thing is, don't put a brand new PV array onto a poor quality flat roof, because when you come to replace the flat roofing in a few years' time, you've got to take all that PV back off again to repair your roof. So it's much better, if the roof is coming to towards the end of its life, is repair the roof, resurface the roof before you put the PV panels on, so you don't end up putting it on, taking it off again. It's much cheaper to repair before installation. And the second thing is to talk about roof warranties. So most of the roof covering manufacturers will have their own requirements for how PV is fitted to the roof, and failing to meet those requirements can lead to the warranty of the roof being made void. So just check what the roofing details the roofing manufacturer needs, and quite often that will mean they'll ask you to put a sacrificial layer of membrane over the top of the actual weathering surface, so that if there are any little sharp edges, or if there are any movement of the PV against the roofing surface through thermal expansion, those kind of things, it's not going to wear through the membrane and cause a leak. On flat roof installations, panels are normally set at between 10 and 15 degrees pitch, and the reason for that is it allows for good self-cleaning from rainwater, and reduces what they call inter-row shading. So if you imagine you've got two rows of panels, the one row in front of another will tend to cause shading of the row behind, and we'll see in a moment. Inter-row shading is a bad thing. Very similar to flat roof is obviously if you're ground mounting a system. So the actual systems look pretty similar. Big difference is that they tend to be used more in commercial installations. So you'll see big fields of solar panels in various parts of the country. But the big difference is they're usually ground anchored rather than using ballasting to hold the panels down. So we've got 3 questions so far. I'm just going to quickly go through them. Panels wired in series or parallel, from Tony. So the individual strings are wired in series, and then the different strings are then effectively wired in parallel to different connections on the inverter. Can you confirm the life cycle period for solar tiles? They're pretty similar actually to normal panels, so it's around 20 to 25 years, but they are obviously newer to the market, so there's not quite so much data to go on as to whether they actually last how long people say they will. And John Leach asked about cleaning of PV panels. Generally speaking, PV panels should be generally kept fairly clean by rainwater, so they shouldn't need to be cleaned too often, but it is a good idea to have them cleaned as part of the annual service of the system, and we'll talk about that a little bit later on under the maintenance tab. Mohammed asked about solar panels that track the sun. As a general rule, they work very effectively. They're very high efficiency. The downside is obviously you're adding a huge amount of complexity to the system for a tracker, and generally speaking, from an economic point of view, the added complexity doesn't pay back in the additional output. So in the UK, the putting tracking in just doesn't make economic sense, which is why you'll see that almost all solar farms have fixed panels. Okay, so just to look at a couple more systems for integration. So this is a roof pitch integrated system. This system is where the panels sit relatively flush with the surface of the roof, and you can see they replace the roofing materials with the weathering system that sits behind the panels. This gives a really nice finish, but it's still very common for new build. Good aesthetic, and they're relatively simple to install because you're still putting big panels in, and actually the flashing arrangements are pretty standard, fairly similar to a Velux window, that kind of thing. But obviously, because again you're trying to fit something into the weathering surface of the roof, you're basically looking at re-roofing that aspect of the building. So it's only really viable on new build or where the roof is going to be replaced anyway. On a new build, the cost is about the same as surface mounted, and that's why you'll see a lot of developers using this technology, because it gives a good return for them. Just worth noting, there is a small performance loss against surface mounted, and that's because the panels will get ever so slightly hotter than they will when they're surface mounted, because the air can't get around the back of them quite so well. That, in practical terms, in the UK, will work out at about 3%. So for retrofit installations, this type of system is much more common. So this is where you put the panels over the top of the existing weathering surface, and then there's hooks that slide under the tiles and hook onto the laths, and that's what actually holds the panel down. But the panels themselves sit outside of the weathering surface, and this requires a lot less roofing work. And is by far the most common system for domestic retrofit. And if you drive around, you'll see lots of houses with this sort of type of system on. It's relatively simple to install, obviously not quite as aesthetically pleasing as an integrated kit, but you do get a small efficiency gain over the integrated kits. Okay, so next bit we're going to talk about is the inverter. So we've talked about the panel. We're now going down to the inverter. So this is the, if you can remember back, this is the box that turns the DC electricity that you're getting out of your panel into the AC electricity that you can use around your house. So what do inverters need? Well, ideally you'd put an inverters in a cool place. They work most efficiently where they go in a cool place. In the UK, most inverters are actually installed in lofts, and that actually is far from ideal, but it's done just purely for space reasons more than anything else. The reason being that lofts see quite a big variation in temperature throughout the year, so they get quite hot in the summer and quite cool in the winter. So ideally, in Germany, their inverters are usually placed in basements, and that's actually totally perfect because you get relatively cool temperatures and it's relatively constant temperatures throughout the year. So that would be the sort of absolute ideal. They also, the other good place you can put them is most inverters are IP65 rated, so you can put them outside. Usually sized to about 90% of the peak output of the array, and the reason for that is one of cost. It's you actually relatively rarely hit the absolute peak, but you will get this thing called clipping. So you'll see the array output going up, and where you'd expect it to sort of hit a peak, actually it will just sort of flatten the top off. But about 90% is the sweet spot for that. So the inverter is in size to about 90% of the output of the array. So say you had a 2 kilowatt peak array, you'd put about a 1.8 kilowatt peak inverter in. When connecting from PV to battery, there's a couple of choices, and we'll look at those in a bit more detail during the winter. Right, so yeah, and the one last thing is inverters lifespans. So I've already talked about the lifespans of panels being about 20 to 25 years typically. Inverters, the lifespan will be a bit less. A good quality inverter will last maybe 12 to 15 years roughly. So you know, sort of more run-of-the-mill inverters, maybe 8 to 10 years. So you'll be looking at 1 or 2 inverter replacements during the life of the panels. Again, that's one of the reasons why it's sometimes better to go for a slightly more premium inverters. They do tend to have slightly better lifespans. So here's a fairly typical installation. So this is an MPPT, which is a maximum power point tracker inverter, and this is what almost all inverters on the market are this type. And the reason they're the most predominant type is they're cheaper than the alternative inverters that employ power optimizers. They're also cheaper than micro inverters, which we're not going to talk about in this presentation. But MPPT inverters are subject to what they call module mismatch. So if you have a string of panels and one of the panels, for example, has partial shading, with an MPPT inverter, what will happen is that effectively the string is only as strong as its weakest link. So if you have one panel which is in shade, it will drag the efficiency of all the other panels around it down, and that's something you get away from, which is the type of inverter made by a company called SolarEdge, which uses power optimizers. You get some of the benefits of power optimizers with micro inverters as well, but as I say, they're pretty uncommon in the UK, so we're not going to talk about them in this presentation. So power optimizers are basically chipsets that sit on the back of each of the panels, and they optimize they move the maximum power point part tracker to the panel level rather than to the inverter level, and that means that you basically get the best out of every panel in the string. So each panel has its own power optimizer. These work really, really well if you have systems which are partially shaded, or where there's complex geometry. So an example with this roof. So if you were using an MPPT system, you would probably have to divide this into 2 strings, because the panels on this roof would see a very different level of light from the panels on this roof, and they might be shaded, for example, if there was direct sunlight coming onto this I think it's Control P. Hope that my pen will now work. So this roof here, will have a different level of light from this roof here. And what you'll find is that when these panels are producing lots, these panels might be in the shade and vice versa. And that will mean that with an MPPT system, you'd never get the maximum output from the system. I've just got to remember what the shortcut is to turn that off. But yeah, so they're good for that type of installation. MPPT, yeah, so they move the MPPT optimization to module level, and because each of the power optimizers talks back to the inverter, if you have one panel that's got a problem, you can see straight away from the diagnostics which panel has a problem or which piece of wiring has a problem, and you can pick that up straight away. Okay, so just turn the turn that off, and there's one further advantage of power optimizer systems, which is not inherent to power optimizers, but the only company that make power optimizer systems, which is a company called SolarEdge, they also allow for automatic disconnection of DC voltage in the case of an arc fault or maintenance. Now, what does that mean in practice? Well, solar panels will always produce electricity when they're in the light. They're not turn off and onable in the same way as most electrical devices are. So one of the dangers, and we'll talk about this a bit more on the safety piece, is that you can have a live cable even when the isolator switch is turned off, the DC isolator switch is turned off. So we'll talk a little bit about batteries. So one of the things about electricity is it's quite hard to store. So basically you have to use electricity at the point of generation. And this is one of the reasons why we get this. We get these quite big fluctuations in wholesale electrical price. So the capacity of a battery is measured, as I said, in kilowatt hours. Typically, batteries are about 5 kilowatt hours upwards. And what the battery can do is it can maximize your self-consumption. So if you're generating electricity during the day, but you obviously happen to be out during the day, you go to work, you're taking the kids to school, whatever, you're not using that electricity. In a conventional PV system, you export that electricity back to the grid, and you'll export it, as I said earlier, about 5 pence per kilowatt hour, typically. In the evening, you get home, you want to use electricity to cook your dinner, watch TV, turn the lights on. And so you're buying that electricity from the grid to do that because your PV is getting dark, the PV is not producing anything anymore. So you're buying that electricity back at about 15 pence per kilowatt hour. What your battery can do is it can sit in the middle of that system, and when you're producing electricity but not using it, store that electricity. And then when you're using electricity but not producing it, you can then pull that electricity out of the battery. As I say, lots of good reasons to use batteries. At the moment, in terms of pure cost, they're about cost neutral. So a battery will last about 20 years roughly, depending on how you operate them, and over the course of that lifetime, if you add up the total cost of each kilowatt hour of electricity that they store, it works out at about 10 pence per kilowatt hour. And obviously the difference in cost between what you sell electricity for and what you buy it back for is about 10 pence a kilowatt hour. So as a rough rule of thumb, they're about cost neutral, but they do have some other advantages. As I say, batteries vary in cost. They typically are around 500 to 1100 pounds per kilowatt hour. The Tesla Powerwall is probably the market leader at the moment, and that sits somewhere in the middle of that range. And for warranties, they're based on charge and discharge cycles and time from installation. So again, typically the battery itself will monitor some of that stuff and be able to tell you what warranty it's got left. Okay, so that's kind of covered a lot of the basic components. So we'll just talk a little bit about the effects of azimuth, which is the angle from direct due south, and pitch, which is the tilt of the panels. So what you ideally want is you'd want a ray of sunlight to travel from the sun and fall absolutely perpendicularly onto the panel that's receiving it. And as we talked about a little bit earlier in one of the questions, there are systems that will allow the panel to rotate to follow the sun trackers, but they're from quite a complex system to employ. They obviously use energy because they've got to have motors that turn things. You've got to have control systems that control them. There's lots of mechanical things that can go wrong with them. So generally, they're not employed. Most solar PV arrays are fixed. So how do you maximize that? Well, you need to think about the actual site itself. Obviously, there might be limitations to the site. This looks like it's actually a floating array, so shading is probably not going to be too much of a problem if it's sitting in the middle of a lake. But it might be that that you can only face the panels one way because of a tree or because of the pitch of the existing roofs on a building or something else. So there are limitations to the site, but ideally you would have a pitch in the UK of between 30 and 40 degrees, and the panels would face absolutely due south. If you lived in Australia, the pitch would be relatively similar, might be a little bit less, just simply because of the fact they're a little bit close to the equator in a lot of Australia. But obviously, being in the southern hemisphere, you'd want the panels to face due north rather than due south. So in the UK, this is a sort of typical sort of how you get your what sort of percentage of your output you might expect to get compared to the ideal. So in the middle here, we've got our due south and 30 to 40 degrees. And so that's these squares here, so 100% here. And then obviously as you move out from there, then you start reducing in terms of efficiency. And as you get close to horizontal, you see at the very bottom, you got horizontal, so you get 84% at horizontal. And at 90 degrees, so if you had a vertical surface, you'd only get 71% even facing due south, and that drops as low as 50% if you're on an east-west split. So you can see that the azimuth and pitch can have quite an effect on the output of a system. So that's the sort of first thing to take into account. The second thing to take into account is actually where you are in the country. So this is the European map that shows, or the European Union's map of how sunlight sort of varies around the country. So you'll see here up in northern Scotland, we don't get as much, you don't get a huge amount of light. But as you go further south, you'll see that the colours start getting a bit darker. I imagine that solar irradiance hasn't been affected by us leaving the EU, so this map's probably still valid. And what you'll also notice is that around the coastal areas, you'll get slightly higher levels of irradiance, and in mountainous areas, you'll tend to get slightly lower. So if you look up in if you look in some of the areas around North Wales, for example, you get these sort of little spots where it's a little bit lower. And that's because you'll tend to get a bit more cloud in mountainous locations, and you'll tend to get a little bit less cloud around coastal locations, and that slightly reduce the effects. Right, so how do you actually connect the system up? Well, I think I've kind of covered this already. But basically, you've got your collector here. It's producing DC electricity. That feeds down this wire into your inverter. Your inverter turns that into AC electricity. That then goes to your consumer unit. If you're using the electricity, that electricity will go off to all the appliances around your house. And if you're not using it, then it would be exported back to the electricity grid. And equally, if your consumer unit is wanting more electricity than your PV is producing, you're just going to import electricity in from the grid. And that is basically how it works. When we add a battery into the system, there's a couple of alternative arrangements. This is probably the most common one and is certainly the easiest to retrofit, which is called an AC coupled system. So here you're taking your electricity in DC from your solar PV, you're passing it through the inverter, turning that into AC. So we got AC here. That then goes into your consumer unit. If there's any excess, that then goes into your battery inverter. So that is AC still here. Then you've got DC going into your battery. And when you taking the electricity out of the battery, it's going from DC there, back out into AC, and then either into the consumer unit or could potentially export as well. So you'll see from this that there's actually quite a number of conversions. So you got a conversion here, you got a conversion here going that way, and then you've got another conversion going that way. And there's obviously a small percentage loss each time you do that. And that is a little bit of an inefficiency. So what are the good sides of this type of system? Well, there's a number of good sides. Number one of which is that you can be quite flexible with the location. So you can put your solar PV, your inverter for your solar quite close to your panels. You can put your battery inverter quite close to your battery. You can retrofit the system easily, and you can size your PV array and your battery however you want, because the inverters don't have to be matched. Downsides is because you're converting from AC to DC and back again so many times, you're going to have about a 1 to 3% efficiency loss compared to the alternative system, and you also require 2 inverters, so it's a bit more expensive to install. So this is a DC coupled system, and this looks a lot more straightforward in many ways. So you have a single what they call hybrid inverter that sits in the middle, which does both the PV and the battery inverter duties. And so you've basically got DC everywhere. This side is all DC, and everywhere this side is all AC. And you're only converting from DC to AC once. So if there's electricity going from the panel to the battery, it just stays as DC all the way through. And if it's going back if it's then going out from the battery to the consumer unit, then it gets converted to AC. And if it's going from the panel straight to the consumer unit, then it's also only converted once. So you get a better level of efficiency. So you think, well, why doesn't every system use this type of arrangement? Well, there's a couple of good reasons. One of which is that the inverter needs to be matched to both the battery and the PV array, so it becomes a bit more of an expensive inverter. And because that battery and inverter arrangement might be tied together from controls point of views, and the PV array is also controlled, so it's less expandable. But there's also issues around potential spares in the future. And obviously the inverter and the battery need to be installed in close proximity, so that means you might have to run DC cabling from the PV cells further than you want to, and those kind of things. And there's also a slight mismatch in the ideal operating temperatures between the battery and the inverter. The battery likes a nice warm environment, typically sort of 25 degrees is ideal, whereas the inverter would like a cooler environment, and you get this slight mismatch from that. So it's there's nothing saying that one system is better than the other. It is very much a sort of installation specific thing to think about, but there's ups and downs of all these things. So just going to touch on island mode quickly. So island mode is not a desert island like we've got there, but it's actually just the ability for the PV installation and a battery installation, if you've got one, to be separated from the electricity grid during a power cut. So typically, it isn't the same as an uninterruptible power supply. So some of you might have come across uninterruptible power supplies if you ever worked on data centers or hospitals or other sort of critical infrastructure. You'll have UPS systems. These aren't quite the same, because there will be a small break in power as the system switches over into island mode, but they give pretty good continuity. But the main reason for having island mode is that if you don't have island mode and the electricity grid goes off, then you also have to switch everything else off in the house, because what you can't have is electricity being fed back down the electricity lines into the grid where somebody potentially could be working on it, because obviously you could then electrocute somebody that's working on the repairing or overhead lines, for example. Because there's electrical separation between the installation and the electricity grid, you have to have your own earth electrode, so that the system is completely separate. Okay, so controls and monitoring. There's only a few minutes left, so there is quite a quick guide, but basically there's an awful lot of systems that are installed and people don't really know whether they work. So monitoring is quite a valuable asset. Good monitoring systems will reduce maintenance issues because you'll be able to see straight away when a system isn't performing to its optimal level. And a good SID system, especially one with the power optimizers I mentioned earlier, also speed up fault diagnosis. With the power optimizers, as I said, you can actually track to each individual panel level what each panel is doing. So if there's a fault with a particular panel, you can see it straight away in the monitoring system. It shows system performance and allows accurate sizing and upgrade to battery storage. So one of the things that we get asked on a pretty frequent basis is, what's the ideal size of battery I should have for my PV installation? And the answer to that is, we can't tell you unless you know exactly how you use your electricity. And that's not just how much do I use in total, it's what times a day do I use it, what's my peak demand, what's my minimum demand, you know, do I use my electricity in the evening, in the morning, do I have a spike at between 7 and 8 a.m. when I'm making breakfast, do I have another spike at, you know, between 7 and 9 p.m. when I'm cooking my dinner and watching TV, you know, how much usage do I have at midday? All those things will affect what the ideal size of the battery is. And what we found from experience is, rather than trying to second guess that, actually one of the best things to do is install your PV, monitor it carefully for a year and see where you're actually using electricity, what times a day you're exporting, what times a day you're importing, and then actually match the battery to that actual real demand. And that way you get the best output from the best payback from your battery, and you don't oversize or undersize the battery. So we've had at least one questions about safety. So let's talk a little bit about safety. As with any electrical installation, PV has the potential to be dangerous. So there are things that we should be doing to make sure that we manage those risks to an acceptable level. So the first and most important thing is maintain the system in accordance with the manufacturer's instructions. And this is something that is really important. The second is to install the system correctly. There are requirements for PV installations in BS 7671, which is the wiring regulations. And also consider additional fault protection above and beyond those required by the regulations, such as DC arc fault detection and panel to inverter isolation through things like Safe DC from SolarEdge. So PV maintenance. PV takes very little maintenance, but does still require maintenance over the course of a year. So you have to clean the panels to maintain performance. So the panels themselves, just usually if you put the panels on to a slope of around 10-15 degrees or more, then they will self-clean with the with rain, especially in the UK. Obviously, we're quite quite a rainy environment. But if you have panels that are horizontal, for example, they do need to be manually cleaned on quite a regular basis. But once a year, it's a good idea to clean the panels just to maintain their performance. Check the security of mountings. Obviously, mechanical things can come undone; they can come loose over time. Believe it or not, bolts actually stretch slightly over time, and torque settings go down. So it's worth just checking the torques on all those bolts. Check the condition of wiring. Things like rodent damage, damage from birds. Although they shouldn't, sometimes cables can degrade over time. If you've used suitable cables, they shouldn't degrade, but it's worth checking that condition. Checking the condition of isolators. Again, isolators can be in quite exposed locations. They can be subject to all kinds of mechanical and weather damage. So it's worth just making sure the isolators are still working correctly, checking that cables are done. And then obviously just use monitoring software to diagnose and fix any faults, which is what this gentleman here is doing. Okay, last little bit before we get onto the summary is about warranties. So typically panels have about a 20 to 25 year lifetime, and they will have during that lifetime what they call a linear performance warranty. So panels don't just work one day and not work the next day. They will degrade over the course of their life. So what the panel manufacturers do is they say, we'll guarantee this level of performance in year 1, and in year 25 we guarantee this level of performance, and that's then done on a sliding scale, so you know what you could expect. They'll also have a defects warranty for usually between 5 and 10 years, depending on the panel manufacturer, and that's basically to cover things like if water ingress, those kind of things. Inverters, 5 to 10 years is kind of the standard length of warranty time. Some of the premium manufacturers will offer up to 12 years, but again, it's kind of a bit of pays your money, takes your choice type of thing. The power optimizers, because the power optimizers sit with the panels and they might be difficult to get to change, they also offer a 25-year warranty on those. And then installation, typically around between 2 and 5 years against defects in workmanship on the installation themselves. Again, that's something to talk to your installer about what they actually offer. Okay, so let's talk a little bit about investment cases. So what you'll see here, this is a graph I've taken from one of the big solar PV installation companies that we deal with on a fairly regular basis called Spirit Energy. And this is their kind of estimated cost graph. And what you'll see is that for a very small system down at this end of the graph, a 1 kilowatt peak system, which would be about the smallest you'd ever install, you can see you've got a fairly reasonable cost of about £4,000. And the reason for that is that that there's a number of fixed costs installing a PV system. So things like scaffolding, where you have to have scaffolding, whether it's a 1 kilowatt peak system or a 7 kilowatt peak system. So that's pretty much a fixed cost. You may need to upgrade the structure, so that might well be a fixed cost. You're still going to have to get some guys there to actually fit the system and commission it, so that's a fixed cost. So there's a number of places where there's fixed costs. So you'll see for a small system, you're looking at a reasonably expensive install. And then when you get to sort of typical domestic size system, which would be about here, about 4 kilowatts, you'll see it's about sort of £5,000–6,000 kind of mark. And then when you get up into bigger commercial installation, sort of getting to sort of commercial sized installations, sort of 7 kilowatt systems, then the cost has risen. But you'll see that even a sort of 6 kilowatt system is only going to cost you twice as much as a 1 kilowatt system. So so this kind of leads me onto the next slide, which is about paybacks. So we've talked about payback, and a well-sized system should give you a payback return on investment of around 10%. And the reason for and the reason I say a well-sized system is that if you dramatically oversize the system, you are not going to get the return on investment that you would from putting in a correctly sized system, because you're going to sell any excess electricity back to the grid at around 5 pence per kilowatt hour. So at that stage, you're then not replacing energy you would have been buying at 15 pence per kilowatt hour with free electricity. You're effectively just selling electricity at 5 pence per kilowatt hour. So you're kind of making your benefit from each kilowatt hour you're producing has gone from 15 pence to 5 pence. Equally, dramatically undersizing the system, as we saw in the previous graph, where you saw that the cost per kilowatt hour is quite a high fixed cost, and then it kind of peters off, is equally bad, because you're not getting the full benefit of having PV, but equally you're not getting the full benefit of you're not saving a huge amount of money either. So that kind of covers the investment cost part. I'm sure there'll be more questions on that as we go through, but we'll just talk a little bit about DNO permissions. So DNO permissions, so that's the distribution network operator permissions. If you're installing a system of greater than 16 amps per phase, then you don't require DNO permission. Basically, for anything else, you will do. If you're doing a development and you're putting multiple small installations in, then it's worth talking to your DNO. They may or may not require permission depending on how many houses it is, what size each array is, etc., etc. But that's one just to give them a call. I'd always say, if in doubt, ask the DNO. The worst they can say is, no, you don't need permission, or yes, can you fill in this form, please? It's and generally speaking, they're pretty welcoming of these installations, but they might put an export limit on, for example. So last bit, we've got a couple of minutes left in the hour, so we'll just talk a little bit about demand and supply. So as you know, electricity has to be used at the point where it's produced, unless you have a battery to store energy in the system. And as we're increasingly moving towards a renewable energy network, then we're going to see more and more non-turn off and onable types of generation. So you can see here, solar, windmills, offshore sort of wind is obviously not turn off and onable. You can't just say, oh, actually we don't need any wind in the North Sea now, so we'll turn that off. So because of this, the wholesale cost of electricity varies quite dramatically during the day. And at times of high consumption, the wholesale cost of electricity will be much higher than you'd pay on a conventional electricity tariff. But at periods of very low consumption and high production, so in the middle of a night in the middle of a windy night, for example, the wholesale cost can actually be negative. So they're actually paying you to take electricity away. So that's where battery storage and being able to export on demand could be quite beneficial. Okay, so let's talk about the top considerations with solar. So number one, fabric first. Number two, consider your consumption patterns. How do you use electricity? Is a battery going to be beneficial for you? Optimize the azimuth and pitch of the PV panels, so you're not paying for something you're not making the full benefit of if you can avoid it. Consider access for maintenance, because obviously you don't want to be, say, for example, scaffolding a building every time you need to get up to maintain your PV panels. Consider the type of collectors and their layout and how it's affect the appearance of the buildings. I haven't touched on this, but there is some guidance from the Campaign for Rural England about how to lay PV panels out for the sort of nicest aesthetics. Consider how the system will be monitored, because as I talked about before, monitoring is really good from a maintenance point of view. Then patterns of import of export from the grid before you consider a battery. Work out how that's going to be, and make sure you've got any DNO permissions that you need, so you don't end up with a very expensive bill for reinforcing the electricity network that you weren't expecting. Okay, so this is how this is the services that Mesh offer. So you'll see that we can support all the way through the whole project life cycle. I'm sure most of you will have seen this slide before, so I'm not going to talk about it again. I don't know how many of you have received an invitation to join the MESHWORK, but this is launching into the general public on the 7th of April. But if you do want to get involved, and I would strongly advise that anybody who's taken the time to join this webinar today, it will be of great interest to you. Then register your interest at meshenergy.com/meshwork. There's some pre-invites going out this week and some more next week, I believe, to people who have attended the webinars for this. Okay, I'm now going to just go through some of the questions that we've got that have come in. So let's go back. There are quite a few. So see where we've got to. Okay. So going up quite a way back. So let's start with a question from Jane. Jane Clayton, thank you for your question. Is access required from annual maintenance? I think I've answered that. Yes, it is ideally, because you need to be able to inspect the panels, clean them, and also do things like inspect the wiring and check isolators and those kind of things. Although obviously isolators should be in an accessible position. Patrick's asked about the drop-off in efficiency of panels. Yes, the linear performance warranties, it varies from panel manufacturer to panel manufacturer what that warranty is and what they expect. But generally speaking, the premium panels have a less of a drop-off than the cheaper panels. So that's one of the reasons for choosing a sort of premium panel over a more budget one. And you talk about the fact that technology will have moved on in your question. Technology has moved on dramatically, even in the last 2 years in solar panels. So if we look a couple of years ago, panels of around sort of 280, 300 watts were the kind of the norm. Now it's nearer 380 watts for the same physically the same size panel, 60 cell panel. Is there any fire risk? Richard asks about fire risk associated with inverters and equipment. There are some risks with PV, and if you Google it, then you'll see that some of the things, most fires with PV come from arc faults, and that's one of the things that the safe DC system that SolarEdge offer or microinverters offers. That's one of the benefits of those types of system. Rob, your question about costs, hopefully that's your question has been answered about the costs. Is it worth using PVTs, which are combined PV and solar thermal panels with a ground source heat pump, storing residual heat in the ground in the summer and drawing it back in the winter? I've seen that type of system used. Whether it financially makes sense for most buildings, it would be debatable, but it's something that we'd have to do a bit more work on. Will they make an efficiency difference to the heat pump during the winter? It depends on how you size your collectors and how much heat you're actually able to store in the ground during the summer. So that's a bit of a how long's a piece of string question, I'm afraid. Question from John about the number of panels needed to make the inverter work. It all depends on the type of inverter and the number of panels and all kinds of other things. So the important thing is you size the inverter to the array that you've got. How can you tell which inverters and panels are the best? Asked John. That's a good question. Things to look at are things like lengths of warranties, installer recommendations, but you know, so especially on the panels, the linear performance warranty that you'll see, they will guarantee a certain output after a certain number of years. What you'll see is that cheaper panels will tend to have more of a drop off in performance than the more expensive ones. But also look at, you know, who's actually underwriting those warranties as well, because you know, if I set up a factory making solar PV panels, I could put whatever warranty I wanted on them if I wasn't going to be around next year. So it's worth just checking checking that. Halla asked about the PV tiles and whether they use PowerPoint tracking. Yes, they basically use conventional inverters. I don't know whether there's a system which allows for either micro inverters on a sort of short string level or power optimizers. That's because it's not something we've done a huge amount of in our work. Generally speaking, people tend to go back to conventional panels unless there's a really strong aesthetic reason to go with tiles, simply on the grounds of cost. Do panels work at all on a shady day? Yes, they will, but the output does drop off. Simon, the big thing is that if you have on a system that uses MPPT, if you have part of the array shaded and part of the array in direct sunlight, you will effectively get the output of as if the whole array was in shade, and that's where systems with microinverters or power optimizers really come into their own. You mentioned earlier that 10 to 15 degrees for pitch maintenance was the optimum then, rather than 30 to 40. So Nada, so 10 to 15 is good on a flat roof because of inter-row shading, and because if you go flatter than 10 to 15 degrees, then the panels don't self-clean through rainwater. But the optimum angle for actually collecting sunlight is between 30 and 40 degrees. Hopefully that table I showed you, which had all the outputs versus azimuth and pitch, kind of answered that question a little bit. Jesse asked about durability of PV panels, especially in single-story public buildings. Yes, we had. In fact, that was something I talked to the PV expert at Bowder about a few days ago. The general rule of thumb is if you've got a roof which is susceptible to that kind of damage, the best option is to just put the panels slightly further back from the edge than you normally would, because it makes it harder for them to be vandalized. But yes, I mean, that is a concern. They are made out of glass. They're pretty tough, but they yeah, they are breakable ultimately. I mean, hailstones and those kind of things, you know, even big sort of golf ball size hailstones won't damage them. But yeah, I mean, obviously, if you know somebody's going out of their way to try and damage a panel, then they will do. Mohammed asked about, would a higher voltage inverter allow thinner wiring? I'm assuming you're meaning on the AC side. Yes, I guess so. But generally speaking, you match the inverter voltage to the voltage you're going to be using around the house. The voltage from the panels into the inverter is set by the panel design and the string design. So that's where that comes from. How much more would a PVT system be in comparison to PV? Rob, I honestly haven't checked the prices for PVT recently, so I couldn't tell you. But it'd be safe to say that they would be fairly significantly more expensive. And as a general rule, the PV efficiency on PVT systems is lower than for a straight PV panel without the solar thermal element. We've mentioned monetary costs. What about the reductions in energy, CO2, and how to quantify that, Richard? The simplest way of working that out would be simply to take the amount of mains electricity that you would displace with your PV system, and then multiply that by the declared CO2 value for each kilowatt hour of electricity that comes from the grid. So that's how you'd calculate that. Patrick's asked about east-west splits to make best use of sunlight, typical peak demand times, morning and evening. This is also the due south optimal azimuth you mentioned. Can you explain the logic and pros and cons of this, please? Okay, so east-west splits. If you have a flat roof and you put an east-west split, and unfortunately I don't have a good photo of this, but what you can do is you effectively create a sort of little ridged sort of roof upon a roof with your panels, with half facing east and half facing west. And that means you can physically fit more panels onto the same area of roof because you don't get any issues with inter-row shading. So if you remember, I talked about inter-row shading where the row of panels in front then shades the row behind because of the sun, how the sun comes down onto the roof. So you get a lower output per panel from an east-west split, but you get a higher, you may get a higher total output on a flat roof because you physically can fit more panels on. Obviously, the cost of installation goes up fairly significantly as well, and whether financially it makes sense will rather depend on the types of panels used and other things, and whether you have to reinforce the roof because of the additional weight and all kinds of other factors, and how much it's going to cost you in additional inverters and the added complexity of wiring, etc. Is a Cornish rocker style solution worth the money? I'm not familiar with that terminology, so I can't. It allows you to change the pitch of the panels throughout the year to improve the efficiency of the panels in different seasons. Amrish, oh yeah, I don't know. I've never looked at it, so that's probably. I mean, I guess theoretically it could be, but are you going to then have to pay somebody to go and change that system over, and how much they're going to cost you? And yeah, I've never done the sums on it, to be honest. Question of Hader about the recording. The presentation will go up on our YouTube channel within the next sort of few hours, once I've edited off the beginning and end of it. If you know how you may add more panels in the future, should you buy an inverter today if your expected future panel capacity, or change the inverter when you add more panels in the future? Amrish, that's a good question. I would always size the inverter to what you've got now, and then probably add an additional inverter in the future, because the chances are by the time you do your upgrade, the type of panels that you'll be installing will be different from the ones you installed today. So it's probably better to size everything correctly for what you've got now, and then add additional inverters if you need to.